got a couple of announcements here. We'll start off with the homework assignment, remember, is due on Tuesday, and then the design project, the final submission for that is due on Thursday. Since you've already done the draft submissions, I'd imagine that the vast majority of the work you need to do in order to complete that project is already finished, 85% at least. What remains is the printed copy of the report, and I give you some guidelines in the original assignment description that I submitted about what I'd like for that. There's nothing that you need to upload. I'll email you if I need to see any files, but between your printed copies of the network map and your printed copy of the reservoir sizing and the write-up, that should be just fine. So refer to the assignment description, and if you've got any further questions, let me know. Today we're going to start on Chapter 15 in the book. It is the methods that allow us to calculate water depths as they vary in a gradual way, gradually varying flow. And so it's the application of Chapter 14 stuff that we started on last time. We're going to continue the example that we had to leave off on during class last time. But before we get into that, are there any questions related to the announcements that are on the screen there? Any questions? Well, great. All the markers are dried out. I will be right back. Oh, there they are. Okay. Here's what we were working on last time. We were trying to find the water surface slope and classify the water surface profile. Now, had we gotten as far as calculating that it's an M1 profile? All right, so what we had found was we'd gone through the process of calculating the normal depth using Manning's equation, and Manning's equation told us that we had 2.717 meters as the normal depth. We used the critical depth equation to find out that it's 1.107 meters for the critical depth. So with those two, we can automatically know that anytime the normal depth is greater than the critical depth, that tells us we've got a mild slope. So this is going to be an M-type profile. And now, at this location of interest, the water depth, Y, is 3.2 meters. And so if you look at these two options here, we've got the mild slope option because the normal depth is greater than the critical depth. And then what we have is the water is actually, the given water depth of 3.2 is above the normal depth. So that puts us in zone 1. So we've got an M1 profile because M based on the comparison of normal and critical depth, and then 1 based on where does this flow depth of 3.2 meters fit inside of those 3 zones. Now just from the diagram we can tell that dy dx is positive, and so it's going to be getting deeper in the direction of flow. So we'll keep that in mind, that it's getting deeper in the direction of flow. Okay, so find the water surface slope is the next step of this process. Find water surface slope. And we can find the slope of the energy grade line, S sub f, using Manning's equation. If we rearrange Manning's equation to solve for the slope of the energy grade line, that works out to N times Q times P to the 2/3 power divided by area to the 5/3 power, and all of that squared. So that's how we can rearrange Manning's equation for S, slope of the energy grade line. And in this case, we know the N value. That's given as 0.033. We know the flow rate. That's given us 31 cubic meters per second. And so the unknown thing here is we're going to have to substitute in the geometry for it being a channel that is 8.5 meters wide And the flow depth of interest here is where it is 3.2 meters, the flow depth. So we're going to want to know the wetted perimeter and the cross-sectional area at that section. Okay, so the N value is 0.033. The flow rate is 31 cubic meters per second. The wetted perimeter is going to be 8.5, which is the base width, plus 2 times the side height here of 3.2 meters. Okay, so that gives us the wetted perimeter. And then the wetted perimeter will be to the 2/3 power. And the cross-sectional area is 8.5 times 3.2, and that is to the 5/3 power. And all of that is being squared. So the slope of the energy grade line, S sub F, is 0.000634. We're also going to need to know the Froude number in order to calculate dy dx. And the Froude number equation is q squared times t divided by g times area cubed. And that gives us Froude number squared. Sometimes I'll take the square root of this, but in the equation for dy dx, it actually uses Froude number squared. So I'm just going to calculate that quantity directly. So the flow rate's 31 squared. T is the top width. Here the top width is 8.5 meters, the same as the bottom width since it's rectangular. G is 9.81. And then the cross-sectional area is that same 3.2 meter flow depth by the 8.5 meter wide channel. And that we cube. Okay, so the Froude number squared is 0.04138. And now finally, we put that into the equation for dy dx. And we saw that last time. It's S naught, which is the slope of the channel minus the slope of the energy grade line divided by 1 minus the Froude number squared. So the given channel slope for this one was 0.1%, or 0.001, minus the slope of the energy grade line that we just calculated, which is 0.000634. And now 1 minus the Froude number squared, where the Froude number squared was 0.04138. Okay, so the dy dx is 0.000382. And that tells us that in the direction of flow, if this is a positive value, since this is positive, that means the flow is getting deeper. Downstream, getting deeper in the direction of flow. So we've computed dy dx, and that's the slope of the water surface relative to the channel bottom. If we wanted to find the slope of the water surface relative to the horizon, of course, we'd also need to take into account S naught.
No, that's the same. Dy dx is the same thing as dy dl.
Yes, yeah. In this instance, the x, we're just saying when it's dy dl, L is the x direction, horizontally. Yeah, so it's the same thing. Here you can see very lightly in gray, it says, what if the flow depth was 2 meters? So just to practice the flow classification, if the given flow depth was 2 meters, that would have been between y sub n and yc. So what kind of a profile would we have then? When it was this way, we had an M1 profile. But what if yn is still going to be the same 2.717 meters, the flow depth is 2.0 meters, and the YC is 1.107 meters. What kind of a profile do we have then? That's right, it's an M2. It's still M because normal depth is greater than critical depth. That tells us the M part of it. And the 2, you can tell from the diagram here, if the flow depth is between the normal and the critical, that's zone 2. And so that's where the 2 component of the classification comes from. Just some practice, because you'll do some of these classifications in the homework assignment that's due on Tuesday. Any questions about this example before we move on to numerical integration? Just practically speaking, the flow depth at locations is ordinarily measured by a gauging station. And there's not very many gauging stations across the country, actually. Here in West Virginia, I think we've got maybe in the neighborhood of about 150 gauging stations. And that sounds like a lot, but if you think about how big West Virginia is and how many creeks and rivers there are, it's actually kind of astonishing to think about that the flow rate is only monitored at 150 of those locations. And so since we only know the flow depth very rarely, we have to have a process that allows us to extrapolate the known flow depth some distance upstream or downstream to be able to predict what the water is going to be doing. And so in senior design, for example, this semester, one of the groups is using a computer model to predict what the water levels will be like during a really big storm, because in senior design they're designing a levee to protect part of a small town here in West Virginia. So the process that we're going to go through, the numerical integration method, is one of those computational methods that's behind the software that the students are using in the design project. You're going to learn the nuts and bolts of how those kind of softwares operate so that you can appreciate when you do come to use them. Now, this is showing a river gauging station as it's actually sort of flooded. Ordinarily, when the water levels aren't quite so high, an attendant could go into this gauging shack here and take the reading off of the float that goes along with the water depth. But in this case, there was so much flooding that the gauging station is underwater, and it's doubtful that it's actually reporting any data at the moment. Let's click on this link just because it's fun to click links, especially when they come from spammers, right? You never know what you're going to get in that case. But this one is going to take us to a USGS website that shows what river gauging data looks like. Let's wait for it to load here. This is showing the Ohio River at Huntington, West Virginia over the last couple of days. And so we can see that the water levels have come down considerably, actually 4 feet in the last week. And I went jogging by the Riverfront Park yesterday, and I noticed that there was a city worker there hosing sediment down off of the concrete bench that sometimes people use when they're fishing. The water levels were up really high over the last couple of weeks, but they were hosing it off because now the water levels are finally receding. You can see at this station here along the Ohio River, this is one of many gauging stations on the Ohio River. For a big water body like that, there's a lot of gauging stations because the Ohio River is really important. But what this mentions is that upstream of Huntington is 55,000 square miles of watershed. So that's how much land drains into the river as of Huntington, West Virginia. Some other things that are interesting is you can see that they've been gathering data there from 1934 to present. And so there's a lot, there's a good historical record there over time. It tells you the elevation of the stream gauge and some other information about how there's flow regulation through locks and dams. So if you do choose to take hydrology next fall, then we'll do a lot more work with analyzing data and looking at how over time the flow rates can be controlled by structures like locks and dams and so on. So that's where we get some of the real world, the actual flow depth information, but most of the locations where we may want to know the flow depth, there's not going to be a gauging station there. It's not going to work out that we've got actual data in the place that we're doing a project. So we have to use a method like the numerical integration technique. And the numerical integration method, also it's sometimes known as the direct integration method. In this technique, the way it's used most often is if you know the depth at one spot and some distance upstream or downstream, you know how far upstream or downstream you're interested in. You're trying to find the other depth. It can be switched around a little bit so that you're solving for the distance, but more often it's where you are trying to find some depth either upstream or downstream. And we're going to be working with gradually varying flow. Again, if it was uniform flow, we wouldn't have to bother, because in uniform flow we can find the depth just using Manning's equation. And it's not rapidly varying flow, that's a hydraulic jump. In this case, it's a gradual variation in flow. And so we're going to apply this process equation and numerically integrate it over the distance between 2 points. And in the process, we're going to calculate the Froude number to put that into the dy dl equation. We're going to have to know the slope of the energy grade line by solving Manning's equation. And ordinarily, we will only apply this technique over a distance between 30 and 150 meters. And this limitation is important because if you do it over a greater distance than that, you're going to run into the problem that I illustrated on the board last time in class, that you're trying to approximate a curve as though it's a line. And if you do that over too long of a distance, then you get inaccurate numbers. And so sort of the upper limit of 150 meters is typically where you can get good data. But you'd use smaller intervals where the depth is changing quickly. So remember that as water flows over the edge of an overflow, like this kind of a situation, as it gradually is decreasing, then it decreases more as it approaches. So I would probably be okay using the numerical integration technique between these 2 points, between 1 and 2, because, you know, it's approximately linear. Maybe it'll be all right to find the new depth downstream or the new depth upstream, depending on whether I've got supercritical flow or subcritical flow. But I would have less accuracy in this method if I was trying to take a depth that I knew here and estimate what is going to be the depth here. Because you'll notice that these are further away, and this is the point where it's starting to change pretty rapidly as it approaches that. So the guiding principle is the smaller the distance between the 2 points, the more accurate this technique is going to be. And so if I want to find out the new depth, then the essence of this method is that I'm going to calculate the properties at the midpoint. And so there's this point here that I'm going to find out what is the depth here at the midpoint, what does the channel geometry look like, what are the conditions at the midpoint, and then I'm going to linearize from that midpoint to calculate the upstream or the downstream depth. And I'll illustrate that process in an example here in a minute. In the example, these are the steps that I'm going to be following. I'll calculate at the midpoint the process equation by finding out what is the distance to the midpoint, what is the flow depth at the midpoint, and if I've got subcritical conditions, then I'm going to apply the process equation upstream. But if you've got supercritical conditions, then the more typical thing is to apply the process equation in the downstream direction so that y2 is the unknown. So you'll notice that this has been changed around a little bit. There's a minus when you've got the upstream condition. You subtract the process equation times the distance between the 2 points. x2 minus x1, that's how far apart the 2 points are. But if it's supercritical, I'm adding that because the y2 is going to be increasing depth. So the steps are, I'm going to find all of these parameters at the midpoint. I want to know the distance to the midpoint, what's the flow depth at the midpoint, what is the cross-sectional area, the wetted perimeter, hydraulic radius, slope of the energy grade line, velocity, and Froude number, all of those at the midpoint. And then I'm going to go through this iteration with guessing what the unknown depth might be. I'm going to hazard a guess. And finally, when my guess depth is equal to a calculated depth, I know I'm finished iterating. So I'll get some output from this process based on my guess. And so let me illustrate that attempt with the numerical integration method. And you can follow along on the computer on this example if you want, but I think that it would probably maybe even be better for this first one at least just to watch the steps that I'm going to be following on the screen. You can see we've got an M2 profile. That's sort of already defined in the depiction that I've put up there on screen. We've got a case where the channel is 5 meters wide and it's rectangular. So we've got a 5 meter wide channel. The N value is 0.015. The slope of the channel is 0.001. And the flow rate that's going through there is 10 cubic meters per second. We can go through and calculate the critical depth. That'll be the flow per unit width, 10 divided by 5, squared divided by g, 9.81. And that's to the 1/3 power. So my critical depth is 0.742 meters. And I can also calculate the normal depth using Manning's equation. Manning's equation is that it's 10 cubic meters per second, 1 divided by n. Then the area to the 5/3 power, where area is 5 times the normal depth to the 5/3 power. And the wetted perimeter would be 5 plus 2 times the normal depth to the 2/3 power. And then the slope of the channel, 0.001 to the 1/2 power. And if I pop that into the solver, then solver tells me that the normal depth of flow is 1.124 meters. Okay, so we know this is a mild slope because the normal depth is greater than the critical depth. That tells me that I've got an M. And then in this problem, the location that I know here at 2, where I know the depth is 0.8, that is between the critical depth and the normal depth. 0.8 is between the critical depth, which is 0.742, and the normal depth, which is 1.124. And so that's how I know it's an M2 profile. So what I'm going to be doing, since it's subcritical flow, I'm going to work upstream, and I want to know 50 meters upstream, what is the depth of the water, that 50-meter distance upstream. Any questions so far on the problem setup? Everybody have a copy of the notes, by the way? All right. So I have a template of the spreadsheet format that I'm going to be using here on the next page in the notes. It's got the definitions of what each row is calculating and the formulas that I'm going to utilize. We're going to have plenty of time for an in-class exercise after this first illustration, so don't feel like you have to begin typing in the formulas and mirroring this format quite yet, because you will have time to do that. Okay, so here we've got the flow rate of 10 cubic meters per second. The channel width is 5. Here's the channel slope. We've got the N value. And this is the depth at the location where I already know conditions. This is maybe where I've measured the depth. All right, so the first step is that I remember from the description here, I want to find the depth 50 meters upstream. And so the The distance between the 2 points is going to be simply 50. That's how far apart x1 and x2 are. I don't have any idea what the new what the new depth is going to be, other than it should be deeper than 0.8. So I'm just going to guess maybe it's 0.9 upstream. And the stakes aren't too high. I can play around with that quite easily. So, you know, if I didn't know any better, I could even just start with 0.8. But since I know it's going to be deeper upstream, I'll select the next value, 0.9. Okay, now x bar means how far is it from the known location halfway between the downstream depth, where I know the 0.8 is the depth, and the upstream location where I don't know it. Since they're 50 meters apart, the midpoint is 25 meters from y2. So the formula here for x bar, you can see, is simply the distance divided by 2. Okay, the depth at the midpoint, if this is the downstream depth and this is the upstream depth, then it will be the average of the two. So it is going to be the downstream depth plus the upstream depth divided by 2. So you can see that we would assume there's a linear variation in the flow depth between 1 and 2, because downstream it's 0.8, upstream it's 0.9, so therefore 0.85 at the midpoint. Area can be calculated as the channel width times the flow depth. So there I've calculated the cross-sectional area if all of this is dependent on this guess. So when I change and play around with that guess, of course, the y bar and the a bar and a lot of other things are going to be automatically updated as well. Feel free to stop me if you've got any questions. Any yet? Okay, wetted perimeter, you can see I'm saying here that it's width plus 2 times the depth. So width of the channel is 5 plus 2 times the guess depth at the midpoint. Okay, so we've got the wetted perimeter. Hydraulic radius at the midpoint is going to be area divided by the wetted perimeter. Now, S sub F bar is applying Manning's equation. I've rearranged Manning's equation here to solve for the slope of the energy grade line. And I want to do that at the midpoint. Let me drag that down so it's a little bit easier to see when I'm over here. All right. So it's going to be the n value times q divided by the area at the midpoint. Here's that area at the midpoint times the hydraulic radius at the midpoint, and I need to take the hydraulic radius, as you can see, I need to take it to the 2/3 power, so I'm going to do that to the power of 0.66667, and then all of that is squared, and that gives me the slope of the energy grade line at the midpoint if this is the depth. Velocity is simply q divided by a. So here's the q that's fixed. That's not going to change during this iteration. And then the area at the midpoint, a bar. Froude number squared at the midpoint. Here I can use the Froude number equation. Okay, so that's going to be the q squared times the top width, and since this is a rectangular channel, the top width is equal to the width of the channel, so it's just times the top width here, divided by g, 9.81, times the area at the midpoint, and I need to cube that according to the Froude number equation. Okay, so now I've got the Froude number at the midpoint, and now here's applying the process equation, this one right here. So that's not what I needed. Okay. So it'll be the slope of the channel, S naught. I need to put the parentheses around that since I'm going to be dividing ultimately. Slope of the channel minus the slope of the energy grade line divided by 1 minus the Froude number squared. So 1 minus this. And that gives me the process equation. And then y1 is going to be, now I have to remind myself that if I've got subcritical conditions, this is my equation to find y1. And if I had supercritical conditions, then I would use a different approach. But here in this problem, we have subcritical conditions since it's a M2 profile at our location, and it will also be subcritical upstream of that. So y1 is going to be equal to this y2 that was already known minus the process equation. So it's going to be minus a negative number, and that will give me a guess value of 0.802. Now, you'll notice that this guess that comes out of this whole calculation chain isn't the same as this one. You know, here I just guessed out of the blue what y1 would be, and then this is the output. The difference between those two isn't 0 yet, and I want it to be 0. So I could either manually play around with this until it's equal to 0, you know, 0.91, 0.95, or I can use the goal-seek to calculate the value very easily. And so let's try that. Let's go into data, what if analysis, goal-seek, and I want this difference to be 0. And I want it to achieve that by changing this guess of the depth. And so I say OK. And I'm getting a strange feeling that there's something wrong with this example. I may have typed in a number wrong somewhere because these values aren't matching up. Let me just double check everything. So if I've got my guess depth of 0.944, if I just happen to guess that, 436, that's fine. This is fine. Huh. I must have applied this wrong somewhere, this last equation here. Oh, times the distance, yeah. All right, so I just had it subtracting the process equation, but I forgot to multiply that by the distance, of course. Okay, so let me go back and redo that. It was y1 is y2, this original y2, minus the process equation here, times x2 minus x1. So x2 minus x1 is that distance there. All right. So now, if I had remember my initial guess was 0.9, so I can go through the what-if analysis and do the goal-seek, where I want my objective to be this is equal to 0 by changing the guess. And I tell it OK. It goes through that over and over kind of calculation. The difference is 0 here. So now I know that upstream depth is going to be 0.945. So if we look at the diagram of the problem here, y1 is 0.945. And that matches what we'd expect. You know, we expected, since this is an M2 profile, it's going to be deeper as we go in the direction of flow. And it's not quite all the way up to the normal depth. You know, the normal depth is 1.124. So if we go far enough upstream from this drop-off, it's going to achieve the normal depth. But we're not quite there yet when we've gone 50 meters upstream from this location. It's still somewhere between the drop-off, which was depressing the depth, and the normal depth, which is up to the 1.124. So this is the numerical integration method. What we just went through was the process of if you know the distance between the 2 points. But you can also use this approach, and if you know y1, if y1 was given, then I could play around with the spreadsheet until I found the distance that gave me this y1 equal to that y1. I set up the spreadsheet exactly the same, but I could solve for an unknown distance. And so let's say, for example, I'm curious to know how far upstream do I have to go for the depth to E be equal to 1 meter? Because I said if I go 50 meters, then my flow depth here was 0.94. Well, how far do I have to go from this location, from where it's 0.8, until the flow depth increases to 1 meter? So let me illustrate how I do that. If I knew that I wanted a y1 to be equal to 1 meter, so now I'm going to play around with the distance until this calculated y1 is the same as that. So I could say, is it 60 meters? Is that how far I have to go until this guess is equal to what I know? Not quite. Maybe is it 80 meters? And so I could keep playing around with it manually, or I can use, of course, goal seek. And this time I'm going to say, keep changing the distance until we've got a value of 0 at the difference between the two. And then applying that process, set this equal to 0 by changing the distance. I must have flipped it. All right. So it plays around with the distance, and now it said you can go 95 meters from where it is a depth of 0.8 until you get to the depth of 1. And it's that kind of approach that I want you to get a feel for here in the in-class exercise. So if you turn your notes again, I've given you a problem that has 2 parts. We have a gate, and so it's an M3 profile, which means supercritical flow on a mild slope after that gate. And I've already given you the critical depth and the normal depth. You'll notice at the top we have a wide rectangular channel, and so that gives us a simplified formula for calculating the slope of the energy grade line. The S sub F formula is there on the page for a wide channel, and we talked about that in our last class lecture. But what I'd like you to do in part A is find out how far is it downstream to where the depth will be equal to 0.55. So we know that right after the gate, y1 is 0.25 meters, and y2 is 0.55 meters. But what I'd like you to find out is what is the length between these two locations. So apply the same process, with the exception that because we've got supercritical flow, in this case you're going to be applying the second of these two equations. You're going to say, well, we've got supercritical flow, so this is what you'll use to solve for y2. So that's part A. And then part B is I suggest that you break that up into 2 parts and find out the length between 0.25 and 0.4, and then from 0.4 to 0.55. And that's just to take a look at is the length that we've calculated in part A so long that we're getting any error. It's looking at how much accuracy improvement is there by breaking it up into 2 sections instead of just doing 1. All right, so following that page in the handout packet I've given you is like a template where you can start setting up that problem. We've got the whole rest of class to do that. It should be plenty of time. We've got more than a half hour. I think some of you will have it finished really quickly, and that's the only thing we've got today for the numerical integration technique, is to work through this in-class exercise. So I'll be circulating around as you set it up, and feel free to ask me any questions.